All right, so let's do an example. I'm going to do number 15 from our textbook. And we're going to see what we can do with work and energy and what we know already. So it shows us a trunk, and there are three forces acting on the trunk, and we're going to just pretend like those are the only forces. Don't get worked up about the fact that there doesn't seem to be a normal force. Three forces applied to a trunk that moves leftward by 3 meters over a frictionless floor. The force magnitudes are 5 newtons, 9 newtons, and 3 newtons. So F1 is 5 newtons, F2 is 9 newtons, and F3 is 3 newtons. And they tell us that this angle here is 60 degrees. It also tells us that this object moves leftward. It moves leftward by 3 meters. That means it's moving this way, right? This is the displacement, is 3 meters this direction. So it says during displacement, what is the net work done on the trunk by the three forces? So this is what they mean by network, W net. I don't really know how fast it's going initially, and I don't know how fast it's going finally. So I'm not going to be able to do this through the kinetic energy. Although W net does equal final minus initial kinetic energy, which is 1/2 m v final squared minus v initial squared. I don't know v final. And I don't know v initial. I might be able to come back and use these later on, but I'm not going to be able to use them now. So to do this, I'm actually going to have to sit here and figure out what is the work done by all three of these, using my equation that the work done by one force is the force dotted with the displacement. So force 1 is this 5 Newton force. Remember, I can do this through just saying the magnitude of F1, the magnitude of the displacement, times the cosine of the angle between that force and the displacement. Well, here I have 5 newtons and a displacement of 3 meters. And then the angle between this force and this displacement is 0 degrees. Cosine of 0 is 1, and so I end up with, and I should have talked about this before with my units, so I end up with 15, and I have a Newton times a meter. Well, a Newton times a meter, so the units for work, and if it's the unit for work, then it's also the unit for energy, because work is just energy being transferred. It's a Newton times a meter, but that has its own unit. It's called a joule, or a capital J. And so this is 15.0 joules. And it's a positive 15. This force is adding energy into my box or my trunk. Work by force 2 is going to be force 2 displacement, or the amount of force 2 times the amount of displacement, now times the cosine between force 2 and the displacement. Well, the amount of force 2 is 9 newtons. The displacement is still 3 meters, but the angle is not 0. So let me redraw this. F2 is up like this, and the displacement is this direction. And this angle right here is 60 degrees. So the angle between the force and the displacement is 120 degrees. Right? Everything needs to add up to 180. So this is the cosine of 120. So if we do that in our calculators, 9 times 3 times the cosine of 120, I get a negative 13.5 in Newton times a meter or joules. And it's negative. And that would mean that it's taking energy out. So this puts energy into the trunk. This is negative. That means it's taking energy out. Or on its own, it would try to make it move slower. It would have less kinetic energy if this force had its way. And that makes sense. It's not helping push this thing the 3 meters to the left. In fact, it's stopping. It's trying to stop this thing from moving 3 meters to the left. And so it makes sense that it has a negative work. Finally, work done by force 3 is force 3 dot D. But I already know what this work's going to be. The angle between this force, which is straight down, right? Force 3 is straight down, and the displacement is straight to the left. And so this angle is 90 degrees. I automatically know that this work is 0 because F3 is perpendicular to D. So when I go through and I write what's the net work, it's going to be the work done by 1, which is 15 joules, added the work done by 2, which is negative 13.5 joules, plus 0, or it's a positive 1.5 joules. That's the net work done on the trunk by the 3 forces. Does the kinetic energy of the trunk increase or decrease? Remember that the work done, the net work, is the change in the kinetic energy, or the final kinetic energy minus the initial kinetic energy. If that's a positive 1.5 joules, then that means that Kf is greater than K naught, or we have an increase in kinetic energy for this object. If it was a negative, if we had a negative 1.5, then that means we have less kinetic energy than we had before. All right, let me do something more specific with gravity. So this is not, I think that we do have a problem that I assigned where something gets lifted up off the ground, but I just didn't go and figure out which problem that was before I made these notes. So let's say we have a block and the mass is 10 kilograms and we lift it up by some lifting force. Some F sub L is our lifting force. We lift it from an initial height of 1 meter to a final height of 3 meters above the ground, and we do it at constant velocity. So constant velocity, when you hear that, that means that the final kinetic energy equals the initial kinetic energy, right? If the velocities are the same, that means the speeds are the same. So they are, and then that means the net work has to be 0. Constant velocity immediately means these two things. Sorry, let me take away that thing and we'll move this down since I'm trying to calculate these. Looking at a sort of a free body diagram here, I've got my lifting force up and my mg down. And so I have a sub y is equal to 0 because I'm doing this at constant velocity. And I can say positive y is up. And so I just end up that the F sub L minus mg equals may, which is 0. So my lifting force has just got to be equal to my weight. My displacement is 2 meters up. And so if I go and do the work done by my lifting force, I can say, well, the lifting force is in the upward direction, right? This should be this, but that's going to be the lifting force times y minus y naught, and then the angle between these is 0. And so I end up with just mg y final minus y initial. If I look at the gravitational thing, and I look at it just strictly from the actual definition here, I'm going to have f sub g, which is mg, and I'm going to have y final minus y initial. That's my displacement. But here, gravity is down and displacement is straight up. And so I have a cosine of 180. And so this ends up being negative mg y final minus y initial. Or I can rewrite that as mg y initial minus mg y final, the work done by gravity. Now I could go through and do lots and lots and lots of examples using gravity, but I want you to I don't think you want to see that, and I think we may do a couple more where this will come out, but I'm going to go ahead and let you know that the work done by gravity is always this equation. It's always mg y initial minus mg y final. Or you can bring those y initial and y final, the mg, out and write it like this. This is always the gravitational work done. The work done by the gravitational force is always this. Does that make sense with what we found over here when we had a zero gravitational work? When we had the friction lab, we said it was zero gravitational work in this friction lab because our y initial and our y final were the same here. Right? Y initial equaled y final. So when you go and you do y final minus y initial or y initial minus y final, you get, oh goodness, I got really ahead of myself there. Here, if you stay, if objects y initial equals y final, then the work done by gravity is zero. Right? It doesn't have any displacement in the y direction. The only thing that matters with gravity is if it's changed the height. If you've changed the height, then there'll be some gravitational work done. If you haven't changed the height, then gravity hasn't done any work. And that kind of makes sense because gravity works along height. It's trying to make you go from a higher height to a lower height. If you go against that, if you have y final, which is greater than y initial, right? You go higher. Your object ends up going higher, then that means your gravitational work is negative. Gravitational work didn't help you here. Gravity's actually trying to stop you. If your y final is less than your y initial, so your object goes lower, then the work done by gravity is positive. It did add energy to it. All right. How am I doing? I'm good. Let's look at our equations so far, because we do have a lot of equations already. I highly encourage you to have some sort of sheet where you'll have a lot of these equations sort of off to the side as you're doing these problems, because it really helps to sort of consolidate that all in your mind. So the work done by one force, one lone force, is just that force dotted with the displacement. The force vector dotted with the displacement, you can write that in terms of the magnitude of the force, the magnitude of displacement, and the cosine of the angle between the force and the displacement. Again, where you'd have some force vector and some displacement vector, and then this would be the phi, the angle between them. The net work done by all the forces, so W net is the work done by all the forces on an object. And this thing is equal to a lot. It's equal to a lot of different equations. There's a lot of ways to calculate W net. W net is equal to, just like we just did in that example where we said how much work does one force do, how much work does the second force do, how much work does the third force do, where we use this, essentially, these equations to get that. You can do that. It also has to be equal to, if you knew the net force, if you actually knew the actual net force, say you know that the net force on an object is this, not the individual, but the actual net force. But then the displacement on the object is this. Then you could use the net force. You wouldn't have to go through and figure out what they all were. If you know the net force already and a problem is given to you, then you can use that and the displacement and the angle between them to use just this. You just say the net force times the displacement, or dotted with the displacement, and that's the net work. The net force is the mass times the acceleration. And so I'm just rewriting this. If instead you knew the mass and you knew the acceleration as a given in your problem, then you could just write mass times acceleration, because that is the net force, again dotted with the displacement. And so you could write that. This looks like mad, but it's the mass times the magnitude of the acceleration times the magnitude of the displacement times the cosine of the angle between A and D, now the acceleration and the displacement. The net work is also equal to the change in the kinetic energy, where the kinetic energies have these equations. And so there's a lot of things that net work is equal to, but because net work is equal to all of these, that means that they're all equal to each other as well. Right? So if you knew the change in the kinetic energy from a problem and it told you the displacement, you could figure out what the net force is, because you would know these and you would know that, and you could get the net force. Not only are they all equal to net work, they're all equal to each other. And so this becomes a lot of things that you kind of have to keep in mind. All right. We've said that the work done by kinetic friction is negative the magnitude of the kinetic friction times the displacement. Remember that work done by any force that is perpendicular to the displacement is equal to 0. The work done by gravity is mgy naught minus mgy final. And in fact, this mgy, just as we had 1/2 mv squared, ended up becoming the kinetic energy. Mgy is called the potential energy from gravity, and it's capital U sub g. It's a potential energy. The higher, so this is not, that's just one of these. So mgy, just one of these terms, is how much mass, how strong is gravity, and how high is it? And the larger y becomes, the more potential energy you have. And so we can write the work done by gravity as the potential energy initially minus the potential energy finally. This is actually negative delta, the change in U sub g. It's negative because delta always means the final value minus the initial value. But here we have the initial value minus the final value. So the work done by gravity is this. But you can also write it in these terms. You can write it in terms of the potential energy, where the potential energy due from gravity is capital U sub g mgy. All right, I'm going to do this next one in the next video.